So the title of my talk being From Theory to Innovation and Back Again, I want to get a little provocative today. I wanted to take sort of a look back since the time that Joe was talking about with the writing of taking science to school in the middle of the Onoff 2005, 2007, and to pick up on some reports that were generated out of the National Science Foundation that I want to say many of those recommendations that are very, very important don't seem to be seeing the light of the day. And so it's the idea that, when we have an innovation, to what extent does it gain legs? Does it get taken up? Or does it just get forgotten? And I'll move into that. But before I do that, let me just say that the survey of some of the key words, if you will, from the poster sessions, looking at oral language literacy in science, looking at new course design, looking at flipped classrooms, looking at assessment design, faculty learning communities, teachers' role in supporting modeling, teaching activities and gateway service courses, epistemic gains, epistemic considerations, and small group analysis. You're hitting all the right buttons here. You're really asking the right questions and attending to the particularities of what are important for understanding the dynamics of learning environments. And learning environments being those places and spaces where a learner, a teacher, some curriculum, some assessment all come together. And in this day and age, we know that it's not necessarily in a classroom that has people physically there, but the virtual world is also contributing to that. So, okay, there we go. So the outline of my talk today will be to talk about innovation uptake in both science and science education. I'm going to do that through a substance which has just gotten a lot of play. It's called graphene. And I'll talk then about, as I said, a couple reports from the NSF. The first one was a Wellcome Trust US-UK STEM workforce meeting. There were 3 separate meetings over the course of 2 years. It involved Rising, Wealth Gathering, Storm Report, Tough Choices or Tough Times, a report from the National Council of Education and the Economy. Then there was the NSF Footprint workshop, which was co-written by Andy Anderson, and Andy apologized I couldn't be with you today, but you'll see in a moment that there were others here who were involved. And I'm interested in talking about this notion of scaling, right? Everyone wants to say, well, that's well and good, but how do we take it to scale? How do we get it out into as many classrooms as possible? So I'll speak about pre-K STEM education, and I want to touch base on something that is really piquing my interest now in this world of the next generation science standards. And so the punchline is, in the beginning, either in first grade, kindergarten, second grade, or early on in the grade bands, or at the beginning of a course, whatever that course may be, I think practices are more important than the content. I think that the development of the practices are more important than the initial development of the content. And I'll play that out a little bit as we move forward. So, graphene. Graphene is a substance of pure carbon. What you see here is a single layer of it. This is a rolled sheet of graphene. This is a depiction of the crystal graphite, which we would see at the end of our pencils. And then this is referred to as the fullerene or buckyball. And both this discovery and this discovery earned people Nobel Prizes. Graphene has many uses, and the slide doesn't help you see so much of them, but you can sort of see from the depictions is that there has something to do with, excuse me as I get used to this, something to do with batteries, it has to do with conductors, it has to do with different kinds of composite materials, and so there's lots of hope that it'll impact many areas of industry. But reading this article in December of the New Yorker, which was called The Annals of Innovation, was sort of prompted me to think about how, if this is happening in the sciences, I started to worry and wonder about what it would be like in education. Graphene may be the most remarkable substance ever discovered, but what's it for? There we see the Nobel Prize winners who did something really amazing to read about it, is they just kept taking new pieces of Scotch tape on top of this molecule, and every time they pulled it off, they were getting it in half again, and in half again. And I'm sure their Scotch tape is not the kind we buy in the store. But they were able to actually bring it down to a single atomic thick layer of this material. And it had startling properties. Its mobility of up to 250 times that of silicone in semiconductors. And so the hope was that this material was going to be just hugely innovative and impact our computer science in our areas. But, and it did win the Nobel Prize. And there's been a proliferation of grants around graphene, 3,018 in 2011 to 3,014 in, 8,416 in 2013 in Korea and China, and then also third in the US, and most of that is at Rice University, because that's where the buckyball, where the buckfullerene was discovered. So Rice University threw a lot of money into setting up a center, and so did the British government, because that's where Manchester is. But it turns out that graphene, the problem is, while it can conduct electricity, great, it doesn't have an on-off switch. And so for computers, in terms of the logic chips that we have, it needs to go from 0 to 1, 0 to 1, 0 to 1. But one of the people who wrote about it in the article said that this obstacle of not being able to turn it on or turn it off, the obstacle is not the physical properties, the problem is business. We got a global investment on the order of trillions of dollars in silicon. And we're not going to walk away from that. Initially, graphene needs to work with silicon. It needs to work in our existing factories and production lines and research capabilities. So I start off at the top here with other major discoveries. The element aluminum was discovered in 1820. It wasn't until World War II that someone figured out an application to be used in airplanes. MRI was developed 30 years after scientists first understood the physical reaction, but before the machine began to work. Silicon itself was discovered 100 years before the birth of the semiconductors. So I'm concerned with the innovations, the rapid innovations we're making in understanding learning, learning about the design of learning environments, and operating within a business world that isn't ready to receive us. Larry Cuban wrote a book a while ago about computers and how computers were supposed to be the innovation in schools. And the punchline was, schools won. Schools were not innovated by the infusion of computers. Schools won. So how would we go into, with the innovations that we're dealing with in our research, in our science, begin to think about that? So, yet another one, if you haven't, this is a hot seller right now, I understand it's going to be made into a movie. Merchants of Doubt, two historians of science from Harvard, again, telling us sort of the political environment that we're in with respect to innovation. It tells the controversial story of how a loose-knit group of high-level scientists and scientific advisors with deep connections to politics and industry ran effective campaigns to mislead the public and deny well-established scientific knowledge for 4 decades. The same individuals who claim science of global warming is not settled have also denied the truth about studies linking smoking to lung cancer and coal to acid rain and fluorocarbons to the ozone hole. As one of their experts said, doubt is our product. So this is the rhetoric, this is the spin that takes place in our society, again, around our leading edge knowledge and our innovations. So we have our reports that shake us up every once in a while. I refer to this as the RAGS report, R-A-G-S, Rising Above the Gathering Storm. Not the first time we've seen reports in the United States that have said, the economic imperative, if we don't get our act together, all hell's going to break loose, and we're not going to be a competitive in the world market. But there's other people who argue that STEM education is important because we need educated citizens who are in a democratic society who are going to have to help us make some decisions around referendums that are taking place. Keystone Pipeline is one of them that is really steeped in a lot of science that some people do and do not understand. But then other people will say that it's really, science has been around so long, STEM, and over the last 300 years, that is actually a cultural, that is woven into our society, our culture right now. And it's just important to be a participating person in the culture to know something about STEM. So we've been busy turning out lots of reports, and I think they have really been a set of great reports that have informed our field, beginning with how people learn, knowing what students know. This is the book that Joe's talking about, but we have books about undergraduate education, math education, and America's Lab report about what we're doing in schools. All of these make some exciting recommendations about how we should begin to change our practice and what are some of the new research questions that we need to pursue. So we have our innovations in STEM education. These are even more recent reports from the ones that I just showed you. The monitoring progress towards successful STEM education. This is a plea for, we need new measures, new indicators of what STEM education will look like. And NSF has just made some new awards to sort of get the ball rolling there. Next generation science standards we're all familiar with here, the framework. I was pleased to see in my conversations with people yesterday, today, that the discipline-based education research report was on people's minds, but I guess that's not a surprise because last year we had my former colleague at NSF, Susan Singer, here to talk with you, and indeed she was the person who put together that report. But that's an exciting set of developments now too about moving educational research more squarely into higher education. And then Education for Life and Work, a report chaired by Jen Pellegrino that gets us looking at the different types of skills, 21st century skills or cognitive skills, intrapersonal skills, interpersonal skills, as a part of what it means to be educated in this world today, to be able to function in a way that will be productive. So let's talk about the first NSF report, which is about workforce. NSF is very, very concerned about workforce. It's part of its mission of preparing the nation's next generation of scientists, mathematicians, engineers, computer scientists. And in 2001, Sir Roberts was commissioned to do a report for the government in England, and he wrote the Roberts report, SET, Science, Engineering, and Technology, Set for Success, the supply of people in STEM skills. The RAGS report comes out in 2005, making the same kind of claim, overall charges to address cross-cutting issues in the science and technology policy that affect the health of the national research enterprise. So this is the Committee on Science, Engineering, and Public University Partnerships or something like that. It's the highest level committee within the National Academy. We have the Board of Science Education, we have the Board of Testing and this, but this is the one that is, the CEOs, the presidents of the universities that come together and really set the broad-ranging policy. And then shortly after that, this report on National Center for Education and Economy came out with some recommendations about really, if we don't as a nation turn our new technologies towards deepening our understanding of creativity and people with imagination. Lots of people have written about this, is that, the jobs that, much of what we do in school is preparing students for a set of skills that are now capable of being done by machines. And they're not getting the skill set that moves them outside and beyond, those particular kinds of lower level jobs these days. So, in England as well, a report led by John Gilbert as the editor with many others, started to set out these kinds of issues about, what's going on. And these translated pretty well to what's happening in the US. And so Sir Roberts wrote to the director of NSF and said, I noticed you got this report. Would it be helpful if we got a contingency of people together with your people from the United States, and we sat down and began to brainstorm about what we might do together in solving this particular problem? Transforming America's scientific and technological infrastructure. I wasn't aware of this report until I started to prepare this talk. And I was surprised to find out that there's this thing called Project Kaleidoscope. And it was done in 2006. And what's interesting, and I find it kind of telling, and maybe part of the issue here that I'm raising, is that, in 3 years there were 20 reports. In 3 years there were 20 reports that came out of Washington area agencies, like how people learn, knowing what students know. And they were trying to summarize for the field the impact that it was going to have on higher education, not K-12. For the reform center dedicated to empowering STEM faculty, including those underrepresented. So, some of my colleagues are aware of this, and for those of you who haven't, this was a study that was not done in the United States. You won't see the U.S. on the column of the names of countries. And critics say, it was a study that wasn't really well done either, because some of the statistical procedures were found wanting. But it really, nonetheless, sent a tremor across the world that we better do something different with respect to science education, because we've got a problem with these dates. This data, rather. So the ROSE stands for Relevance of Science Education. It was conducted by Sven Solberg from the University of Oslo. He contacted individuals in each of these countries around the world. He asked them to get together a sample of people to take the test, students to take the test. And the results, you can see here from a scale of 1 to 4, male and female. And based on the question, do you have an interest in science? Now, this listing of countries is from the low development to high development. Highest development countries, ECO, economic, for the lowest. So look at, just show you quickly 3 of the slides, and you can look at the pattern of what you see. So as we then ask the question, I like school science. The other thing that's noteworthy to folks who are looking at this is the gap between boys and girls in these countries. And finally, I want to be a scientist. So it sets out, the challenge that in addition to, it sets out that in addition to the challenge we have about, the quality of education, is that there's still something going on. And these are our science and technology leading countries. And these are not, and yet the interest of what is being communicated. So the conference, got into these kinds of issues. As I said, we had 3 conferences. The first workshop was coordinated around these 4 themes: supporting and sustaining innovation in schools, attracting and retaining teachers in STEM, attracting and retaining students in STEM, and entering the STEM workforce. Here, attracting and retaining teachers in STEM for the conference, both for England and the United States, was primarily physics teachers. Primarily physics teachers. In fact, England had started a program where they were taking biology teachers and chemistry teachers and putting them through a short course and turning them into physics teachers. They figured that if at least they knew their discipline well enough and had experience managing a class, that perhaps they could, be the best way to sort of bolster the activity there. The second workshop, we went over to England, to their new national center in Leeds, and we were met by many other countries. Now it was no longer just the US and the UK. But what led from that, and this is the innovation part that I'm concerned about, is that we came away from this meeting and saying, should the United States develop a ROSE-type survey and do it right with the right psychometrics? Should we begin to establish a baseline of information that would begin to tell us about motivation, interest, and identity? And as you see here, I'll let you read that. There's currently no existing survey that has done that. It never got off the ground. It never happened, and I don't know fully why it never happened. But at the meeting, when we were talking about this, these other reports started to come and play. The opportunity equation from the Carnegie Corporation, the European Commission, The European Commission had another report on new pedagogy. And Australia was starting to look at the same problem. So, two common themes emerged from all these reports. One is that, in short, as I showed you the data, the more advanced the country, the less people seem to be interested. And two, the approach, and most of them was, rewrite the curriculum. Need better information to understand the conditions and factors for opting in and opting out of STEM opportunities. So, it turns out that one of the things we learned from this is that the demand problem is not monolithic. There's a glut of scientists, postdocs and scientists in PhD biological sciences. There are variant solution paths for the supply problem targeted at attracting and retaining students. And going back to the point I made at the beginning, is the policy agenda varies enormously. Some see it as an economic issue, some see it as a cultural issue, and many see it as a pedagogical issue, where student experiences and incentives and the quality of the teacher workforce aren't necessarily there. So we need to, rethink the sequence, the content, the context. This is sort of what we're taking place with a lot of the work that you're doing here. To enhance and broaden the teacher workforce in the upper grades and advanced place courses. This is something I never really, every time I see that, say, well, we need more people out of industry to come and teach advanced place courses. We need more people out of industry and universities to come and teach high school courses. And it's like, wait a second, if you're not attending to fourth graders, fifth graders, and sixth graders, where people are opting in and opting out and making up their minds, you're really missing the whole problem. But again, it's interesting to see how policymakers sometimes see this. So this is a direct quote at the top from the workshop about what was proposed as the research agenda, and it was, we decided that the place to target was middle school. For what I just said to you, is that by 6th or 7th grade, most children opt in or opt out based on their identity as to whether I want to go into science or not. So I'll let you read that paragraph. So, innovations and change, you know, who are our partners, who are our players, how do we take these things to scale? These are even more recent reports than the ones that I've showed you. The STEM leadership, STEM teacher leadership, literacy for science, STEM integrated education, developing assessments for the next generation science standards, and reaching students at the undergraduate and science level. So if these keep coming out with all of these recommendations, you know, how are we going to see them get to scale? I will propose one problem is what I'm going to identify as disciplinary tensions and mismatches, and I'm only going to speak to my field, which is earth sciences, the earth sciences. So Joe mentioned to you that I worked with the next generation science standards, and when I started to work on that, I found out that there was an attitude among our colleagues in universities and colleges that when we looked at the next generation science standards and seeing all these particular areas, that you know, we had a three-dimensional prospect to learning, and that was going well and good. And then out come these pamphlets at exactly the same time, sponsored by the Department of Interior, sponsored by the Department of Education, in which we needed to have the following earth science literacy principles, space, climate science literacy principles, ocean science literacy principles, and this is atmospheric science literacy principles. Here are the actual dates and deadlines. You can see direct conflict with the development of these other ideas that we're taking on. And you're not meant to read this, but you can probably make out that up here there's more of a cluster of dots and X's. These are the different 9 core areas rather than 4 that are in the next generation science standards. But conspicuously absent is this bottom row right here. And those of you who are close can see that there's a little cluster here, nothing, 1, nothing, 2, 3, 4. Those are the instances related to practices. Everything else is concepts, what concepts we need. So breaking down just for the earth sciences area, within those 9 areas there are those 9 areas across the top. Okay, so now I just printed them out for you. And inside each of them is a set of 7 competencies within that. So this is now just for the big ideas in earth science. There are 66 competencies within that field. And we don't have oceanography, we don't have atmosphere, we don't have climate, and all those other things. So that's a problem. Right? I mean, no, it's a tension. It's, you know, why aren't we getting the innovation? Well, not everyone's on board, right? I mean, that's part of it, is that, you know, recognizing that other people are seeing the world differently than the way we do. And yet, you know, that's frustrating. So, the NSF also then put together a footprints report. So this is very exciting because NSF funds research internal to the organization. And a footprint report, this award was given to Jim Himos and Janice Earl. And with that money, they were given the opportunity to do 3 studies. They do a portfolio analysis of all the work that had been submitted to NSF in the area of learning progressions. They then were able to do as kind of a survey, literature review of that which was outside the field. But then they were also invited to hold a conference. And Andy Anderson with Paul Cobb were the co-leaders. Angela was a part of the process too as a member of the steering committee. And the questions, I'll let you read the 2 questions. Now, I was invited down to NSF to give an oral presentation to the program officers when the draft of my review of the learning progressions paper. And then on the basis of that, I ended up being asked to come and be a part of the particular conference. I was real excited. I mean, a lot of us in this room really see this whole idea of learning progressions and coherence and sequences. It's just one of the most powerful things that can take place. For those of you who aren't necessarily familiar with the essence of this, let me give you a good example that most people seem to be familiar with. So at the elementary grade level, you either have, as a teacher, experienced, or perhaps as a parent, the school districts that order the kits. You know, you get a big box of science equipment, and so there's different kits and different companies produce these kits, and it's a very effective way to help a teacher, get the science and hands-on into the classroom. But they're expensive. These kits are expensive. And so, you might order for, say, 4 kits for K2, 4 more kits for 3-5, and then maybe another set of kits for 6-8. But, Bob, you're going to start with kit 1, I'm going to start with kit 2, Melanie's going to get kit 3, and Renee's going to get kit 4, and then we'll swap. Duh. What kit you get second is going to be influenced by the kit you got first, and so forth and so on, so that there is no coherence and no sequence to the learning. And that's what we're trying to get away from by promoting this idea of learning progression. So these were the issues that were coming to bear, and the recommendations for the report were that, additional research on learning progressions needed to be made. And boy, I certainly agree with that. Relations among curriculum instruction, teaching, and learning progressions need to be pursued. Concerns related to equity and diversity need to be pursued, and relations pursued. And, and Amelia and Alicia had a very early LEAPS report that was pulling a lot of this together. There was a special issue in the Journal of Research in Science Teaching, which I like the LEAPS report a lot because it was sort of an edited volume. But personally, I thought they were jumping the gun with a special issue on learning progressions at a time when we really didn't know what they were. I mean, there was some good work in some particular areas, but, to this day, I'm still confronting and feel that I have to, straighten people out and say, well, that's not quite what a learning progression is. I got lots of colleagues at Penn State who would say, well, I'm doing learning progression research. And what's that? Well, I'm looking at, what goes first, what goes second, what goes third, and then we'll see, and then we'll manipulate that. So sometimes things get away from us. So the recommendations are to have additional research on learning progressions, look at the curriculum and its infusion, equity and diversity, relations with learning progressions between mathematics and science. So there were 6 major areas of recommendations in the report. I'm only going to highlight 2 of them just to stress the idea around standards and assessment. So in the standards area, the participants in their conference saw great potential in the dialogue between learning progression researchers and the developers of the standards. Now, I was the developer of the standards. Joe was the developer of the standards. And I would say Joe and I had a good sense of what people were sort of getting at with respect to learning progressions. And even though the next generation science standards says that they are about learning progressions, it's not really there. The rhetoric is there, and then the matrices in the back where you have the grade bands K2, 3, 5, 6, 8. You can begin to peel some of that apart and then begin to talk about it. But we got a lot more work to do to sort of understand that process. Amelia and I were with an unnamed group about a month ago down in Washington. It was all hot to go out and do some things about learning progressions, and we're just like, really? That's what we think they are? And so people are ready to run with an idea, before it's actually there. That doesn't help our innovation, our implementation, when people start to, see it in different ways. So, I do agree that the development affords an opportunity for dialogue. This is very important, I think, and that's what's nice to see about some of the work you're doing back here, is you're reaching down to the very early grade levels, is that the learning progressions do really fundamentally predicate on your understanding where the learner is at the starting level. And the word that's used is it accessible to the learner? And you can ask that question when you're 5 years old, 10 years old, 15 years old. If you're putting cards on the table for a course, are the cards you're putting down accessible to that person coming in at that time? If not, you're not getting the sweet spot, or you're not getting where you want to be. But we can learn what that is. That's the point of doing some of the foundational work for this. Contributing to practices and cross-cutting themes, I think that's important. And contributing to disciplinary core ideas. Longer term, the report goes on to say that, and this, I always thought this, is that we got to get away in this country from thinking that the standards we put forward are etched in stone. We've got to have a flexible system. You have to have a mechanism that says every 10 years, or whatever the date is, we're going to go in and we're going to rearrange and think about what's different. And we need to be able to have school districts and state departments, recognize the fact that we are learning about learning. We are learning about how kids do better, what's more effective. And so there needs to be a mechanism. And this report recognized that different, but they also said that there's different timelines for research and standards development. Research findings, come out intermittently. Standards development enactment requires clear timelines, and they need to be stable for a period of years. Criteria for validity. When can learning progressions research findings be considered sufficiently generalizable? It's sort of site-based or place-based kind of specific. Some arguments are being made. Learning progressions research commonly has more to say about the order of concepts than about the grade levels. This is another big bone of contention because, as we find out again from the work with the younger children, is that they are more capable. It really has a knock-on effect of changing what it is we do with kids in middle school and then what it is we will do again in high school. Because some of the work is getting done at an earlier grade level. So again, it perturbs the system in ways that have to be perturbed, and it can be positive in that way. So, going further on the longer-term considerations, to consider the role of learning progressions research in the enactment of standards, 2 recommendations for new roles in research approaches. One is people in bridging roles. We need people, perhaps learning progression researchers, who are familiar with the standards, with the learning progression research, classroom practice, and professional development. We need to figure out how to educate those people and to support their work. We need the people who can, work both sides of the street, so to speak, as to what's taking place there. 2, we need short turnaround time for the research. Local implementation of standards will often require kinds of action research that use learning progression findings and methods, but has shorter timelines and specific local application. So to sort of, get it going and to build our understanding. Assessment. Recommendations for assessment. 3 areas of discussion of assessment emerged from the conference. The development of the assessments itself, with learning trajectories and research, the measurement models that will be used in developing those assessments, and understanding the potential negative effects that the assessments may have on using learning trajectories research. And I spoke with a couple of people yesterday and today about, for me, I think that this is a very keen area. And I know that some of you are developing assessments and looking at the way that the students respond to them. But this takes us right back to the assessment triangle, knowing what students know, and being able to, we can't provide good feedback to learners, we can't mediate learning, we can't have good scaffolds unless we really understand and have tasks that make that thinking visible, that make that kind of information that's there. And that's a robust area of work to get done. And I encourage people to think hard about that. Learning progression researchers have often devised interesting and creative tasks and tools. This is what we're getting at. They demonstrate how the intermediate understandings of children can be powerful and rich for discourse. This is a plea that, sometimes an idea is worth working with rather than saying that's not right, it's wrong. In terms of the response to a misconception or an idea. The glass might be half full, let's work on what half full. I'm reminded of a great line that I heard from Brian Reiser, a lot of people in the room know that, when he said, someone said, well, kids get all confused about, the motion of the moon and the earth. And he said, one kid says, where does the moon go at night? And he says, it goes down behind the mountain. And Brian said, yes, but at least we got motion. And in other words, there's a platform from which to begin. At least that moon is moving, and now we can build from there. So learning progressions could help to meet a key challenge in our current assessment practices, the need to design methods for examining students' progress over extended and varied periods of time. And then also looking at, the role of technology and wireless devices could provide opportunities for studying new forms of assessment over real-time data. And, in that arena, the future is now. There's all kinds of companies that are presenting tools where you can have data dashboards on student learning. And so teachers are given a graph, a dashboard, here's how your students did, in some cases they're told, here's the lesson plan to implement tomorrow. I mean, they're really taking out of the hands of teachers some of the important decision-making that needs to be there. So those kinds of practices are ones that perhaps need to be studied by our community as well. So suggestions for specific studies are this comes in the appendix of the report. So there's been a lot of interesting work done on measurement. And so the report suggests that 1 or 2 carefully chosen experimental programs of learning progressions that have the potential to cross disciplinary backgrounds. So go across science into math into engineering. By investigating a common topic core to all of them. And where we already have some detailed research to initiate that process. To also do a district level experiment, like the kind that was hinted at before, is pick a small school district in terms of size and attempt to create a coherence among the standards in all those areas and then study it along the way. So this report on learning sciences is available from Studies in Science Education. The 2 reports that I just talked about on the workforce and the footprint are on the conference website, for this conference website, as well as the next topic I want to talk about with innovations in education, how long to take root, is this idea of these practices. So practices, as I was saying, I'm very keen on those and wanting to see how they get developed. It is my predilection that content has always come first. We've always said, what do we want students to know? What do they need to do to know it? I like to flip that around. What do we want students to do? And what do they need to know to do it? And when we get to some of these practices, if we want them to engage in modeling, if we want them to engage in argumentation, if we want them to engage in cause and effect explanations, if we want them to engage in certain quantitative reasoning strategies. Some disciplinary topics are better to do that than others. And so that's kind of the point that I have. But from the framework, and this is also now the guiding principles for the PISA 2015 structure, is that there's going to be assessments around content knowledge, procedural knowledge, and epistemic knowledge. For our psychologists in the room, this procedural knowledge is not the procedural knowledge that is used by cognitive scientists. It is, however, the methods that scientists use to find their findings. So, Christine knows this story because when Brian asked me to participate in a new book that NSDA has coming out, they said, would you like to make a contribution to the dimensions and the practices? And I said, yeah. I said, I'd like to do that. Well, the one they gave me is the one highlighted in blue, and that would have been the last one that I would have picked. But because it was given to me, and it was given to me at a time when I was trying to work through a presentation to the state science supervisors who had helped put together the next generation science leaders, and more often than not at those meetings I'm asked to talk to them about issues of nature of science. I started to think about how planning and carrying out investigations in nature of science, planning and carrying out investigations in nature of science, and I hit upon this idea, in my head at least, that if you unpack the process of planning and carrying out an investigation, to do so in the way that you problematize measurement, you problematize the tools that you're going to use for measurement, you problematize how you're going to record results, you're going to problematize how you're going to represent and structure the data and the patterns, and you're going to engage in a reflection on determining whether the data were good, you had enough of it, or if a new instructional design was there. As I started to think about that more, I started to think, okay, there's some modeling in there, there's some argumentation in there, there's some explanation in there, and our teachers, as many of you know, are confused about a lot of the practices that we're asking them to engage in. What is partially familiar, if that's even the right way to put it, is that from 1996 with the NSES, National Science Education Standards, with an inquiry focus, teachers across the country have a fairly strong orientation towards teaching science as inquiry and doing through the processes of investigations. So it's my conjecture that one of the ways to get to the 8 practices of science and engineering practices from next generation science standards is through this unpacking, and that's the point I made in another paper that again is up on the website for this conference that I just published with Roger Ivey, is that rather than fusing practices, we're making the argument that this one gets unpacked, and unpacked in a way that will make it a little more obvious for some teachers as to how, there's all this decision-making taking place. And the reason that is, and you don't need to see this, but this is sort of how planning carrying out goes across the investigations. I want to get to this part here. So the framework also says, importantly, that our students have gotten a steady diet of investigations which lead them to believe that science is straightforward. You always get the answer. Experiment always works out, unless you drop a flask. It's just, it sort of seems to work that way, isn't it? It's groovy. But what the framework says is that we need to rethink, the way that our investigations are put together. And some people have written about the importance of productive failure, right? In other words, a problem is so complex that you're not going to get it the first time through, You're going to have to show some grit and persistence to sort of work your way through it. Maybe you have to go, Lord, you may have to go and work with some other people and compare notes, you know. You got to think about that. Scientists never do that, do they? I think that again, the unpacking of the planning and carrying out investigations by problematizing these different areas will help get at what they call in the framework the struggle of science. Science is a struggle. It's hard. Building the knowledge, refining it, it takes time. It's not straightforward. And so Susan Carey and Carol Smith have developed this interview protocol, out of which they get level 1. Here, people see knowledge as unproblematic. Students view scientific knowledge as a collection of true beliefs about how to do something correctly or as basic facts. Transition to level 2. Students view science knowledge as a set of tested ideas. Notions of explanation and tested hypotheses appear at this level. And at level 3, we get knowledge as problematic. Students see scientific knowledge consisting of well-tested theories, models, but the theories are seen as guiding inquiry, and evidence for experiments is not only used for hypotheses, but the theories as well. Theories and models are also seen as more or less useful, rather than strictly right or wrong, and knowledge of the world is fundamentally elusive and uncertain. And so it's that kind of a process that we want to have. Let me finish up by posing several challenges to you as a field. First challenge is we need to get a common language in our community. We use lots of different terms for the same kinds of things. Challenge number 2. This has been around since 1995. It was a talk given by Robert Glazer, in which he said that there are 7 things that we know from psychological research that have implications for how we design practice, and I think we need to still go deeper into many of these things. One of the conclusions is that knowledge has a structure. We know the importance of prior knowledge in learning. We know the importance of metacognition. And here's where the other procedural knowledge is used. We know that procedural knowledge, in meaningful context, helps for learning to be connected. But on the social psychology side, we know that social participation in cognition is important, learning with others, learning in groups. We know that a holistic situation for learning, sort of like a cognitive apprenticeship, so that you're deeply immersed into a particular problem space, so that you're going to have to reason around that. And then finally, one that, sorry, did I lose it?
Battery.
Battery?
Computer battery.
Does this go dark? No, bottom.
Anybody have a charger?
That was the second to the last slide, so we won't worry about that. So I want to say that we're doing important work. You are definitely doing important work here at Michigan State. You've assembled an amazing group of people to be part of this. You have international scholars coming into the center. Is it a center? Or an institute?
Crazy Institute.
It's an institute. You have international scholars coming in the institute. You've got postdocs in the institute. You've got enthusiastic graduate students. You've got great faculty. I wish you all the best on your endeavors with this. And work hard at this work, because we got a lot of work to get the innovation into the schools, hopefully in our lifetimes. Thank you.
So we have about 20 minutes for questions. So if there's questions, raise your hands and speak loudly so everybody can hear it. questions? We got a question back there.
I'll get this.
There's a question.
Yes, sir.
You alluded to it indirectly in your talk, but I wonder if you could speak for just a little bit about how you see the role of informal education in this whole process.
So the question was, how do I see the role of informal education in this area? Well, I think it's important. I think it's very important, and I've been involved in those conversations. So, you know, part of what's really important for our learners is to have experiences as they're growing up. And when we think about the diverse experience that, and I'll have to link it back to the classroom, that if you have a classroom of 20 or 25 kids or 30 kids in a classroom, a teacher has an enormous set of resources in those children and in the experiences that those children have had outside of school. So opportunities for our youth to have opportunities in museums and zoos and aquaria, to be available to the media, the movies, the shows, the television programs that are dealing with science, all of which constitute sort of an operational definition of what we mean by informal science education. The NSF would say it's anything outside of school. Anything outside of school becomes a possibility. So we are, to the extent to which our youth can have access to these other learning experiences, and then the extent to which a teacher knows how to tap into that with respect to conversations that take place in the classroom, it really helps benefit everyone. Joe?
So Rick, I couldn't help notice that the first point in Robert Glaser's 7 or 9 points there had to do with the importance of structured knowledge.
Yeah.
And that if we're really going to have people learn, the goal is to help people make connections and structure their knowledge in a particular way.
Right.
And that's what allows them to actually make more connections.
Right.
Well, that to me is the major premise behind the framework and the notion of core ideas, right?
Yeah.
That's the premise, right?
That's right.
And then I reflected on that laundry list of stuff in the Earth Science group that you put up there. Now, I just wanted you to comment a little bit on, so the goal of the framework was to really take that point that Glaser made about the importance of structured knowledge and really try to come up with the core ideas that are supposed to build across time. And when I looked at that list of stuff from, not to be offensive to my Earth Science colleagues, but it seemed like they weren't paying attention to that point that Glaser made.
Right.
So I just wondered if you would comment on that. I mean, that's what I saw when I saw it there. I saw Blackwood, and to me that's the importance of trying to bridge these worlds together.
Yeah. Well, they didn't listen to the title of each of those pamphlets. The common word was literacy. So the target was for undergraduate programs. But like a lot of things, people take something and try to use it in other places. And that's kind of what happens with some of our colleagues in higher education that, and that would certainly be the case for my colleagues in Earth System Science, is that, climate literacy is real important. I mean, it's an ongoing dialogue around here, but it's not an easy problem. And it's certainly not knowing the kind of literacy points that are there as much as it is understanding the way in which scientists go about modeling, creating these climate models and dealing with the concept of the uncertainty of data. And the uncertainty of data doesn't mean the data are uncertain. The uncertainty of data, which is a terrible label for them to have, just means we don't have enough of the right data. That's what the uncertainty means. Not that the data we have is inaccurate and wrong, but we don't have enough of the data gathered that enables us to really draw upon the model, but people don't respond to it that way. So, so when you're making decisions about, and I'll call it adult learning now, right? If you're going to say, you know, here's the kinds of things adult learners should know in this pamphlets for literacy, because they were passing those out to all the undergraduate faculty who would be teaching Geology 1 or Oceanography 1, and that was their main point, but it just spilled over, as you know, into our world in terms of, well, these, we already know, we scientists have figured it out. These are the big ideas that take place there. But we have another community now that's emerging, which is the science of learning, or the learning sciences, that begin to tell us a little bit more about, again, like I said before, what's the sequence, what's the coherence, what's accessible, where do you begin to start, what's the design of the assessments that will let you know that learning is progressing, and progressing in the way that you would like it to. That's a very different game. Yes?
Your comment about the common language and defining those terms. So somebody who wants to find definitions to the terms, what resource would you send them to?
Well, I don't know. See, these are kind of terms where we're like definitions don't really apply. You know, I mean, maybe that's one of the reasons we get into get into trouble there. I don't know. It's kind of like, maybe it just comes with the field. Is that, you know, when you're a researcher and you want to coin a term, and then someone else wants originality, they're going to coin the same concept but use a different term. And pretty soon, you know, we're talking about developmental pathways, learning progressions, learning trajectories, coherence and sequence in education. And they're all basically the same thing, but they apply to sort of different areas. And we have lots of terms within our respective fields that describe things. So like the procedural knowledge one, you know, the person who was putting that forward for the framework, when I was asked to read the draft, I said, you know, this term's already taken. I said, you know, there's a whole field that uses this term in terms of disciplinary knowledge, procedural knowledge. If you go to the 2009 NAEP framework for science, you will find procedural knowledge used in the psychological range. Now that right there in and of itself is just, you know, that confuses people, right? That's being a way. So we need Bob to become the arbitrator. Now that he'll have so much time with not having to work on a journal, we can become the arbitrator of things STEM linguistic. Thank you.
We still have another poster session, so please stick around for the second half of the poster session.